So let's get some practice using this fully vectorized approach to solving dynamics problems now. And so we're going to be applying this to a simple pendulum. This is the normal way that you see a simple pendulum, in which the mass located at point P is hanging below the attachment point. And we're going to solve this first with Cartesian coordinates in an inertial reference frame. So first, let's define that reference frame. And here we have three basis vectors, E1, E2, and E3. And E1 is defined along the line of gravity, E3 out of the page, and then E2 being the cross product of E3 and E1. We've already drawn our gravity line, and so let's set up our coordinates. We've decided to use Cartesian coordinates, so we have x in the horizontal direction, or along E2, and then y in this vertical direction, which is along E1. To solve for the dynamics in this system, we need to apply Newton's second law, and the vector form of Newton's second law is F sub p, meaning all the forces that are on particle P, is equal to the mass P multiplied times the acceleration of P. And remember, Newton's second law only works in an inertial reference frame, so we have to define our acceleration as being observed in the inertial reference frame. And so to do this problem, we're going to take each of these components, all the forces on P, we'll find out what those are, and then we'll find this acceleration of P, and then put all these back into Newton's second law, and then solve. So let's start with the left-hand side, which are all the forces on particle P. First, we draw a free body diagram of our mass, and we apply all the forces and draw those as vectors onto the point P. And so let's start with the force due to gravity, which is mg. Now, we're in a vector notation now, so that means that all of our forces need to have both a magnitude and a direction. And so the direction of mg is pointed along gravity, which is along a positive E1. So we write mg in the E1 direction. Now our next force is a constraining force, and we'll call it F. And what this is doing is keeping the particle P onto the slender rod. Now F needs a direction. We've drawn it here in pointing back to point O, but we haven't defined exactly what directions those are in terms of E1 and E2. So we'll just leave this as a vector F. But what we can do with this constraint force is that we can proportion it in the E1 and E2 directions. And so we do that by looking at the distance y, which is our Cartesian coordinate, and then the actual length L. And so the component in this vertical direction is going to be a proportion of y over L. So it's the scalar magnitude F, y over L. And then the way that we've drawn this is pointing up, and positive E1 is down. So that means that this is negative F with a proportion y over L in the E1 direction. Likewise, if we draw the E2 component as a proportion of F and then x over L, then this component is pointing to the left, and that's opposite of E2, and so this would be negative F multiplied times x over L in the E2 direction. And so now we can determine what F sub P is, which will be the sum of these three forces. And because we've already written these forces in vector form, we transfer them over to this representation, and we just add them up to each other to get the sum of the forces on point P. Now let's find the kinematics that are going to the acceleration of P as observed in the inertial reference frame. We always start out with the position vector. So here it's r, P with respect to O, and this is equal to x in the E2 direction plus y in the E1 direction. The velocity of P with respect to O as observed in the inertial reference frame is x dot E2 plus y dot e1. And then, of course, the acceleration of p with respect to O as observed in the inertial reference frame is x double dot e2 plus y double dot e1. We plug all of this in to F equals ma, and after this we equate coefficients for the E1 direction and the E2 direction. Now I see that I neglected, when working with the kinematics here, to define the kinematic constraint that's part of the problem. And so that is x squared plus y squared is equal to L squared. And so in summary, what we have here are two second-order equations. And these two equations, when combined with our constraint equation, give us a single degree of freedom system that describes the motion of this simple pendulum. And so what we've done is we've taken an example that you've seen before and then worked this using our full vector notation to get a feel for what's going on. So don't forget to define your reference frames and define them explicitly, and then write down the governing equation, in this case Newton's law, second law of mechanics, and then start filling in the sides, the left-hand side being all the forces on the particle, and the right-hand side, the most complex term that you have, is the acceleration as observed in the inertial reference frame.